Hi there, my name is Dr. Barry Blight, and I'm a lecturer in the School of Physical Science, and we teach chemistry, physics, and forensic science, and I'm an organic chemistry lecturer. Today I'm going to speak to you a little bit about some luminescent materials that we've been developing, and I'm going to talk a little bit about where luminescence is derived from and how it works. So if we think about luminescence, there are three different classes. We have photoluminescence, okay, which is effectively the excitation of a material with a wavelength, some wavelength of light, and the emission process that we see is the fluorescent colors, much like when one goes to the club and you see a black light shining on your t-shirt. So we're using a wavelength of light to excite a material in your clothing. We also have chemiluminescence, where a chemical reaction is the result of a photon being emitted, which is the visualization of light. And so what happens is, for instance, glow sticks, where you break the little glass rod inside of a glow stick, and you shake it up, and you see that chemical reaction, and you see a nice, bright, vibrant fluorescent color. Similarly, with fireflies or glowworms, you have a chemical reaction happening in the tail, and that luminescence process is literally two things coming together and creating light. And then we also have electroluminescence, which is effectively excitation, like shining light or a reaction happening, but coming from current, just like in your mobile phone, for instance. So that emission of light is by running a current through the pixels of your LEDs, and that energy being put in, you're seeing come out in a different form or in a different color. So luminescence, though, is derived from molecules and the energy being put into molecules. So if we take our atoms, for instance, we know that atoms have electrons, and we know that atoms have orbitals, and the electrons sit in the orbitals. As soon as we combine the atoms, we create molecules, and what happens with the orbitals is the orbitals combine to create molecular orbitals. And in the orbitals, we have electrons, and we have full orbitals, electrons full with orbitals full, and we have orbitals that are empty. And when we excite the electrons into the orbitals, the electrons relax, and what we end up getting is an emission event. So basically we have our paired electrons, and they get excited up into the empty orbitals, and when they relax, we get our emission of a photon or our fluorescence. And fluorescence specifically is when we're using spin paired electrons. So electrons have opposite spins, one gets excited and then relaxes again. And because the electrons are spin paired, that process is very fast. We can see that down to a few nanoseconds. Now if we think about phosphorescent materials, or materials that are glow-in-the-dark materials that we all know and love, that process is obviously much longer. When we turn off the light, that emission happens for a much longer time, and it can happen on the order of microseconds to hours. And basically what's happening is we have our spin-paired electrons, and when we excite our material, the electron goes up into the empty orbital, but it also spin flips. And that spin flipping process takes time. And then when we have our relaxation process, we also have time the process takes time to relax again. So it has to spin flip again and return. And that process obviously allows us to see the emissions of the photons for much longer periods. Oftentimes we can use transition metals or heavy metals to make this process more efficient and a little more bright as well. So luminescent materials are actually extremely useful and we use them in organic LEDs. Obviously, I showed that in our phones, our tablets, and our computers. Photochromic materials, so people who have transitions glasses, for instance, those are photochromic materials where you have a chemical reaction. When the light shines on it, it changes the orientations of the molecules, which changes the color. And that's what happens when you walk in and outside. We have photochromic materials, so vapochromic materials, so materials that respond to different vapors. And then we also have chemical sensors, in which fluorescence of one color changes as soon as we add some type of analyte, which is what we're going to look at today. So one of the materials we use in our lab is Bacillus Anthracis, and it's a very useful, or not very useful, a very scary material. Obviously, we've had the anthrax scares in the United States in 2001, which have resulted in increased awareness of this bacterial spore, Bacillus Anthracis, and that's what causes the disease anthrax. The bacteria is an endospore, okay, and it can resist very intense environmental conditions. So effectively, what happens is it's a bacteria in a shell, and it's protected from heat and light and other types of decomposition. But as soon as it hits any kind of moisture, the bacteria gets released. And so in the presence of about 10,000 spores, if you inhale 10,000 spores, that type of dosage can be fatal. Dipicolinic acid is a material within the endospore itself that comprises of about 15% of the dry mass of the spore. And basically what happens is the dipicolinic acid binds with calcium ions to create this shell-type polymer that encapsulates the spore. And as soon as you add water, the polymer dissolves and releases the bacteria. And work done in the Ponce group has shown that actually they have a very nice turn-on sensor for this material by taking dipicolinic acid, adding them to a lanthanide metal called terbium, which turns on the emission. So as soon as it comes in contact with dipicolinic acid, it turns bright green. Now, they did studies using europium, which is a different lanthanide metal, and found that it wasn't very useful. So what we thought we would do is maybe instead of using a turn-on sensor, is use a very dramatic turn-off sensor using this type of idea. And the way that lanthanides work is very similar to the way I described the fluorescence a few minutes ago, except that for lanthanides, the process is actually a forbidden process. You need to have organic ligands around it in order to facilitate it. And this is because emission of lanthanides without the organic ligands is a Laporte forbidden process. And in order to do that, we have to make the environment around the ion dissymmetric. And so we can do that by adding organic ligands. And as soon as we add organic ligands around a lanthanide, we then get an emission process, or an excitation process, that occurs through the ligand and then is funneled into the metal through a ligand to metal charge transfer. But then the emission occurs out of the transition metal. So we get this antenna effect. And this funnels the relaxation process through the d orbitals of the lanthanide. The best way to demonstrate the antenna effect is by doing a little experiment. So if we can dim the lights a little bit. So if we take a material like a naked lanthanide ion, we can see that it's not very bright. It's very dimly lit. But as soon as we add an antenna ligand, where the absorption of this black light happens through the ligand, it will then funnel the energy into the metal. As you can see through this very dramatic experiment, that we can see a very nice bright emission process happening. And just like adding a dipicolinic acid to the sensor that we're going to develop, we can kill that emission by adding some other material that can compete. So if we add a little bit of methanol, we can see that we can turn off that bright emission process. And in a principle not too dissimilar to that, we thought we would try and develop a new sensor for Bacillus Anthracis. In our teaching labs in the School of Physical Sciences, we actually synthesize a very simple europium material using very simple chemistry. And in fact, it turns out that it is the red emitter in your mobile phone. As you can see here in this funnel that one of the students have made, a very bright red glowing material. In the spectrum, it emits very deeply into the red, and you can see on your phones what red looks like. And this material is no longer being used in the OLED industry, but it's still a very useful material. It's very cheap to make, and it's very easy to make. And so we thought this might actually be a very nice system to develop a sensor with. So before we went and did any type of specific analysis, we thought we would look at the absorption of our material. So if we take our system, our europium complex, and we add a little bit of water, we can see that the absorbance goes down. Now the reason why we're looking at using water and phosphate is that in bacteria there's water and there's phosphate, and these are obviously synonymous with biology. Phosphate is a form of energy through the form of ATP. It's also in DNA. And so by ensuring that our material actually functions in the presence of these things is quite critical. So we add a little bit of water, and we can see a little bit of decreased absorption of light, which will obviously affect how our emission process happens. But that's okay, because it's just a minimal bit of absorption. We can see here with water or with phosphate, we get a similar decrease in absorption. But as soon as we add our dipicolinic acid, you can see that we get a very dramatic change in the absorption spectrum, which is very good. It means that our material has a very specific response to the addition of dipicolinic acid. And we also did the experiment in the presence of water and phosphate, and then added our DPA. And you can see, again, a very similar response, though shifted a little bit because there are more processes happening. And similarly, we decided to take a look at our emission spectrum. And so fluorescence, the color red, this is what the color red looks like in a graph, okay? It's around 620 nanometers is the color red. And you can see here, as soon as we take our dipicolinic acid with our material, we get a very distinct decrease of emission. In fact, almost completely eliminates the emission. And as soon as we add water and phosphate, we can see that that doesn't inhibit the process at all. In fact, it enhances the process. So it's a very effective emission sensor for Bacillus anthracis, well, at least for dipicolinic acid, which is in Bacillus anthracis. So here's a very simple visualization of what's happening. We take our molecule and we dissolve it in some organic solvent. And then we add our dipicolinic acid. And you can see that we get a very distinct elimination of fluorescence. You can see that in water and in phosphate that the emission is decreased, but the emission is still there. And similarly, in water and phosphate together, there's still a decrease in emission. But then as soon as we add our dipicolinic acid, we get complete quenching of our fluorescence material. Now, obviously, one of the most important things about these types of materials is being able to have very high sensitivity. And so by being able to look at very low concentrations of the dipicolinic acid is very important because we don't want people being exposed to significant amounts of this material. So if we take a look at our emission spectrum down in the nanomolar region, which is about 10 parts per billion, we are looking at very distinct quenching of our fluorescence with water and phosphate. But then if we add dipicolinic acid, we can see a much greater response in that emission decrease. So that means that our material is not only quite effective sort of in a bulk state, we can also see very distinct changes down at very low concentrations, so in the nanomolar or part per billion range. So this makes it quite a sensitive sensor as well, which we're very pleased about. So hopefully you've gotten a little bit out of this lecture. I've managed to describe to you a little bit about where luminescence is derived from, and then looked at how we can use this type of material to sense dipicolinic acid, which is the biomarker for Bacillus anthracis, and then looked at sort of what happens in the presence of water and phosphate, what happens when we add our dipicolinic acid, and obviously looked at sort of some detection limits for this type of material. So thank you very much.